In this lecture, we'll be looking at the Schrodinger equation in spherical coordinates. So far we were in one dimension. Now we're going to introduce three dimensions. So our variables, independent variables are r, theta and phi. So this is essentially, we're setting up ourselves to solve the hydrogen atom. That's why we're introducing spherical coordinates and we're introducing three variables, independent variables. So here you can see that the Schrodinger equation is written out in spherical coordinates. So this is how it reads in spherical coordinates. Now we solve, this is a partial differential equations in three variables. So we'll try solving this by looking for solutions of the form given here. Now the technique used here is called separation of variables. So I encourage you to look up this technique of separation of variables, which I won't be detailing here because we are actually going about trying to solve the hydrogen atom. But even I'm doing a series in mathematical physics where I will detail the technique of separation of variables. So in the separation of variables technique, we write out this, we separate the r coordinate and the angular coordinates into two different equations, and we substitute this solution of this form into this equation. When we substitute that, we get this set of equations. So here, this equation, now what we'll do is we divide that equation by y and r. So y and r are this is the angular solution, this is the radial solution. We divide that by that y and r and we multiply it by this factor here. So when you do that, we get this equation. Now here you can see that the variables have separated. So this term now is only containing the radial term and this term contains the angular term. So it is the practice in separation of variables technique to write these two terms equal to some constant. Okay, it's called the separation constant. Now this constant, we write it out in this form. Normally we just take a constant, but we writing out in this form because it is because we're setting ourselves up to solve the hydrogen atom. That's why we're writing it out in this form. So you can see that these two are written out with respect to some constant. Now why we write this as plus and this the same constant as minus, you can see here from this equation itself. Now this equation contains only terms of r, right? So when this r changes, there is no dependence of r here, right? So this for a change of r, there should be some corresponding change of theta so that this equation sums up to 0. Now since there is no dependence of interdependence because the variables are separated, we name this, we call this function, this set of this term in the curly brackets, we say this is a constant, right? Because and this is the negative of that constant. That way both will be, sum will be equal to 0. So this is how we write, this is a separation constant. This you can actually read up in the separation of variables technique. This will be detailed quite well there. The reasoning will be detailed well there. So next we have to solve each part separately. Now we've written out the angular, this is the radial equation, this is the angular equation. Now we just have to solve each part separately and we'll get the solution of the problem. So that's what we'll set out to do now. So the angular equation now just becomes, so the angular equation, this equation we are taking and we are multiplying it by this factor. Okay, we're multiplying it by this factor. When that we do that, it becomes this equation. Now again, what we'll do this, you can see that this is a partial differential equation in two variables. So we'll again use the separation of variables technique and look for solutions of the form that are separable. One function of only theta, one function of only phi. Now when we plug this into this equation, this solution into this equation, we get this equation. So now we again employ the separation of variables technique. So you can see that this term is completely separated. You can see that this term has no dependence on theta and this term has only theta dependence. So you separate them, write them equal to some constant, separation constant. So that is what is being done here. Two equations are separated, written out equal to some separation constant. Now let's solve each of these equations. Now we'll take the 4.21. That equation we'll try to solve first. This equation now, the solution for this equation is nothing but an exponential, because if you take an exponential of this form and take the two derivatives of it, you will bring out the m square down and you'll get the phi original solution back again. So this is the solution for this equation. And in our original problem, we had said that this phi is a, when this phi advances, you can see from the problem here, when this phi advances by 2 pi, it comes to the same point in space. So this condition also has to be taken into account in the solution. So when pi advances by 2 pi, it becomes back to the same point. So that case m can only be an integer. So that case m has to be an integer. So that's why this is m takes a integer value 0 plus or minus 1 plus or minus 2 likewise. Then we have to solve the theta equation. So the theta equation is written out here. Now this theta equation is actually, in our mathematical physics series we learned few special functions. We'll be using these special functions all around. We've already used a lot of special functions to solve, for example, the harmonic oscillator problem. We had used the Hermite polynomials. So this is a kind of a special function. This equation, differential equation, has a solution. Has a solution called the associated Legendre function. So this is called a special function, and this is a constant, just a constant. You can find it out. All these constants are found out using the normalization condition, which we'll do later on. Now this PLM, and it's a function of cos theta. Okay, so here we have x. Now when you plug in the values of L and M, here you can see the values of L and M, it will automatically generate the corresponding function. So P of L has a particular function, and that means just that when you L can take some integer values, right? So L can take some integer values, 2, 3. So for each value of L, there is a corresponding Legendre function. So this P of L is called the Legendre function. So P of L is called the Legendre function. P of L. Handwriting is very bad. I'll have to improve. P of L is called the Legendre function. And once you plug that in, you just take these derivatives and you just do these operations. You will get the associated Legendre function. Now we've solved the angular part. We solved the angular part for theta and phi. We solved and got solutions. Now we're going to solve the radial part r. Now the radial equations reads this way. We had already written out got the radial equation by separating the variables. Now we simplify this radial equation by using this new definition. This r and small r and capital R are defined as u of r. Okay, such that the equation gets redefined in this way, and now this reads like a this reads very similar to our Schrodinger equation, right? This reads very similar to our Schrodinger equation, except for this term, right? Except for this term. Now that term is actually the centrifugal term. So this is V is the potential, and this extra term here is due to the fact that in our problem we had seen that, we go back to the diagram. Now problem, you can see that this is the radial term. Now when there is radial motion, what happens? There is a centrifugal force, because of which there is a centrifugal potential. So that extra term denotes the centrifugal force. Okay, centrifugal potential. Now we're going to set ourselves to solve the hydrogen atom. Now in this place we have to insert the potential for the hydrogen atom. The potential for the hydrogen atom is just a Coulombic potential, the Coulombic potential between the proton and the electron. So we just write it out and we substitute it. Now the solution for this, it's from here onwards to solve this is actually a very lengthy process, and again the solution is in terms of a special function. So I'm just going to tell you what special function is that. We had seen about the associated legendre function. Now we're going to see about another new function called the logger function. We're going to see about the associated logger function. So you may again look up that function in a mathematical physics textbook. It would have been solved, and this is the this type of equations, differential equations, give us the solutions in terms of associated logger polynomials. So that is what we will do now. So the solution that you get for the radial equation is of this form. Oh, oops, sorry. Okay, is of this form. Now here this L of Q. Okay, this L of Q is actually the logger polynomial. Just like you saw the legendre polynomial, this is the logger polynomial. This logger polynomial again can be generated. I'll show you how it can be generated. Logger polynomial. Now you have a suffix q. Now what the suffix q means is this can be generated using this equation. So this is generated using this equation. This L of LQ is generated using this relation. You just have to plug in the value of Q. So the Q can take some value, some integer values. Okay, so Q takes some integer values. Okay, some integer values. So when you plug in that value, you automatically generate a function, and the associated logger polynomial is it requires two integers. It requires p and q. Okay, so here you can see p and q, right? So let me point it out using. So here you can see p and q. So once you specify the q, you get the associated logger polynomials using this function. So when you do this operation on the logger polynomials, you get the associated logger polynomials. Now the solution is, it already solved the radial. This is the solution for the hydrogen atom. This is the complete solution for the hydrogen atom. This is the solution. So I'll explain how we get these terms. So this term that we was talking about, associated logger polynomials, is here. You can see it here. Now in the place of q, you have 2l plus 1. L is the azimuthal quantum number. We had introduced it as the separation constant. And n, now this q minus p is here. You can see it as n minus l minus 1. Now this L is the principal quantum number. It is introduced in the course of solving for this equation. Okay, in the place of Q, not Q actually. In the course of solving for this associated logger polynomials, we introduce the integer n, and that takes the place here. And this, in the place of x, we have 2r divided by na. Okay, so r is the radial coordinate, and a, you can see, and a is a quantity called the Bohr radius. Okay, the Bohr radius. So it has a value 4 pi epsilon naught h square m square. So this quantity is called the Bohr radius. This a is called the Bohr radius. So these are these terms, and this y of lm we are already seen as the angular equation solutions were already obtained, and these terms, that is this term, from this term to this term, we actually get using the normalization conditions. We had introduced some constants each time when we're getting some solutions, so we have to normalize both the the radial function and the angular function. When you normalize that, you'll get this this term factor in front of these two solutions. So, and in the course of solving for these solving for the radial equation, we get the energy value, the uh, energy value corresponding to the principal quantum number n. So for when n is equal to 1, you just have to substitute for the value of n is equal to 1 and substitute all these values that are given here, and you will get the answer. So correspondingly for n is equal to 2 and 3, so this corresponds to for the state n is equal to 1, 2, 3. Okay, you can find, and so on, even 4, 5, 6, whichever the higher the state, you can find out the corresponding energy values.